So a major application of integration is, or rather, I guess, a major application of finding antiderivatives is the fundamental theorem of calculus. It's by no means the only one. Like if you have a velocity function, there are a bunch of reasons you might want a position function that are not finding net changes. But of course, it's a big one. And the fundamental theorem of calculus, or half of the fundamental theorem of calculus, can be stated like this. I mean, we don't always think of it quite that way. When we're integrating a function, we don't really think that we're integrating a derivative. We just think that we need to find an antiderivative to use the fundamental theorem. But this is what it says. And there's an assumption baked into this, that on this interval from A to B, the function, I guess I should say f prime of x, the way I've written it here, is continuous. And well, I guess the really important thing isn't even, or the thing we're going to relax at any rate. As part of being continuous, it shouldn't have any vertical asymptotes. So something like the integral from 0 to 1 of 1 over x dx. If you just looked at this and didn't give it a lot of thought and just waded in with the fundamental theorem of calculus, well, the antiderivative is the natural log. And then you would go to your calculator and you would type this in, and you would get an error because the natural log of 0 is not defined. And what's going on here, the reason we're having this issue is that this limit of integration is a vertical asymptote. There are a lot of situations, at least in sort of pure mathematics, like pure analysis, where you want to relax this assumption, where you want to be able to write the integral from 0 to 1 of 1 over x, even though, even though we can't, the way we've approached things so far. And when you have an integral like this, where there's a vertical asymptote at, at one of the limits of integration, or just a vertical asymptote in the middle of the function, in the middle of the interval, it's called an improper integral. Actually, what I wrote on here, I was this is actually, I mean, it's an error, but it's actually sort of a nice error because your calculator will tell you that something's gone wrong. Compare that to this. We cannot use the fundamental theorem here because there's a vertical asymptote smack between these limits of integration. There's a vertical asymptote at 0. But this time, if you just blunder forward and use the fundamental theorem, your calculator won't give you an error message. Your calculator will give you an answer. And this answer is also an error. Now, the calculator isn't spitting out an error message, but we've made an error nevertheless. So it's really important, now that we've introduced this idea, it's really important to be aware of what the function is and what the limits of integration are and what the function is doing between those limits of integration. So improper integrals actually cover a few cases that are pretty distinct from each other. I won't say literally unrelated, but the textbook calls them case 1, case 2. I don't remember which case it thinks is which, and that's not standard terminology. Other textbooks would use different numbering. But to start with, we're looking at the case where we've got an integral from a to b there's a vertical asymptote somewhere on the interval from A to B. And this case breaks down into sub-cases because the vertical asymptote can be, in a few different places. It can be at A, it can be at B, or it can be between A and B. But we don't really have to learn 3 different cases. The first 2 cases are very similar. So how might we define this integral? Well, we've seen this many times by now. It's kind of the way calculus works. First, we could try to approximate this, and then we could try to make our approximation better and better until we make it exact by using a limit. So that's the process that we've seen multiple times now. And let me go to Desmos and let's take a look at this graph. Let me share this real quick. So in terms of area, is that, can you see that? Is that? window from this angle, it's a little hard to see, but graphically, we are looking for this area. And it's not intuitively obvious whether this area can exist or not, because this region we're looking at extends forever. You know, it goes up and up and up. So if we assume that maybe this does exist, we could ask, how can we approximate this? And what we might come up with is that, well, the zero is causing a problem. If instead of the zero, we had a number that was a little above zero, there would be no problem at all. This is, I'd have to go quite far up to see it, but this region does have an upper bound. It's just a finite area. We can use the fundamental theorem of calculus. There aren't any issues. And then we say, well, this might approximate what we're looking for. It's certainly not what we're looking for, though. You see this white band here. How can we make it closer to what we're looking for? And well, how can we make this closer to what we're looking for?
You could make it like 0.000.
Yeah, so if this white band that we want, what we don't have is the problem, and if instead of 0.1, we have 0.01, we see that white band has become a heck of a lot smaller. Now it's smaller still, and again, there's no problem here. This function is defined, it's continuous on this interval. It has a finite area. We can use the fundamental theorem of calculus to find the area. So we can find all of these. And in terms of calculus, what we're doing here is we're taking a limit. We're looking at this lower number and we're making it closer and closer to zero. Properly speaking, it's a one-sided limit, but we don't really need to worry about that. We're replacing this zero with some number, and we're making that number closer and closer to zero. So we're doing this. And now we'll ignore the limit until the very end. This integral we can take now, the natural log of the absolute value of x evaluated from n to 1. Gave myself rather more room than I needed there. Is the limit as n approaches 0, the natural log of 1 minus the natural log of, again, we're properly speaking, taking a limit from the right, so we don't really need these absolute values if we don't want them. And now it all sort of depends on whether we know what the natural log looks like. The natural log of 1 is 0. Remind you of algebra, that's perhaps been a while. The natural log has a vertical asymptote at 0. As it approaches 0, y goes down to negative infinity. So the limit as we approach 0 doesn't exist. Or if we wanted to, we could say the limit as we approach 0 is negative infinity. I mean, either way, we cannot subtract not a number from 0. If we want to think of this as negative infinity, then 0 plus infinity is infinity. Either way, this limit does not exist. Remember that a limit exists if it's approaching a finite number. So our intuition in this case was satisfied. I mean, well, I shouldn't say our intuition, the intuition we might have had that this integral shouldn't exist because, speaking physically, this is the area of an infinite region. This region never stops, it goes up forever, and it might seem very natural that an infinite region should not have a finite area. But in our next example, we'll use this exact same logic. With the integral from 0 to 1 of 1 divided by x squared. And you came in a little late. The point of this problem is that there's a vertical asymptote, that one of the limits of integration. 1 divided by 0 is not defined. And the way we're approaching this, we're approaching it using limits. We say, well, 0 is a no, do you know? I think this is also not going to exist. I think if I wanted to exist, I should have put the square root there, but we'll see what happens. We're saying, well, this 0 is a problem, but if we replace 0 with something that's kind of close to 0, like 0.1, that problem goes away. And then, yeah, definitely isn't going to exist, that's fine. Then we'll let this get closer and closer to 0, and we'll see what happens in a limit. So I'll use very proper notation here, where this lower limit is starting to the right of 0 and it's approaching it from the right-hand side. That's what this plus means. So I've taught this class many times, but I still always have to think about the integral, the antiderivative, when I've got a power in the denominator. That's x to the negative second. We bump -2 up, it becomes -1. We divide by the new power. There's our antiderivative. And now I'm going to delete that so that I have some room to write. So because n is approaching 0, but n doesn't equal 0, we can divide by n. We can divide by any non-zero number, so there's no problem with just sticking 1 in there and sticking n in there. And now, as I prophesized, this limit does not exist. You know, obviously, this is a pretty informal way of writing it, but as n is going to 0, that fraction is going to infinity. Okay, but third time for sure, I'm not messing with you. It is possible for these limits to exist. For these integrals to exist, for these areas to exist. And here's one that does, 1 over the square root of x. Let's see, square root of x, we're going from 0 to 1. And one thing we're seeing, well, once we've verified that this limit does exist, it's basically impossible to just look at a graph and know the answer to this question. You know, this region and this region obviously look very similar, but one of them has a finite area and one of them has an infinite area. Same logic. We can't really look at 0. 0 gives a division by 0 error, but we can look at values that are close to 0. And then we can look at what happens in the limiting case. No matter how many zeros I add here, I'm not creating a problem. This is a non-zero number. We can divide by it. This has a finite area. In formal mathematical terms, what I am doing is taking a limit. Again, I have to think about these. This is 1 over x to the 1/2, so that's x to the negative 1/2. I bump this up by 1. We get -1 plus 1 is 1/2. I divide by 1/2, I get 2. So we've got this limit. We can stick 1 and we can stick n in, no problem. And now n going to 0 does not cause a problem. In fact, everything is continuous. We can just stick 0 in here. The square root of 1 is 1, the square root of 0 is 0. So this time we get a finite number. This time we get 2. So it's not the most intuitive thing, but it is true that you can have regions that are in some sense infinite. It's infinite in the sense that if we keep going up, this region is never going to cut off. It just extends up forever. But even though this region is in one sense infinite, it has a finite area. It has an area of 2. And you can get some quite unintuitive results from this if you mess around a little. You can get Gabriel's horn, a infinite solid that has a finite volume but an infinite surface area. So you could fill it with a finite amount of paint, but you could not paint its inside. We can't go into the details of that because surface areas of solids of revolution was one of those things that didn't seem worth the week or whatever that it would take to do it. But yeah, this is important, and it's going to have, well, maybe not this type of improper integral specifically, but improper integrals in general are going to have real-world applications that we'll see, and they'll have applications in the second half of this course as well. You can probably imagine, I mean, here the vertical asymptote was there at the beginning at A. I mean, you can probably imagine that if it's at B, nothing is going to change in any very significant way. The integral from 0 to 5 of 1 divided by x minus 5, for example. Well, now 0 isn't a problem, but 5 is a problem. So we have to take the limit as we go to 5. This limit's turned into a left-hand limit. Just from the picture. Ooh, cannot see with that sun in my eyes. 1 divided by x minus 5. We're looking at this area from 0 to 5. So it's something's wrong here, though. know, let's see. I'm say we're looking for the area under it. This is actually a weighted area. This is negative on this interval. So what we're actually looking for on Desmos. There we are. Our Zoom window was very messed up, but after a little tinkering, this is the area we're looking for. It might exist, it might not exist. It's not going to exist, in fact, but you know, we're now starting close to 5 here. And we're getting closer and closer to 5, and we're seeing what happens. And what's going to happen is that this is not going to exist. Do not forget that limit. I would scold a student if that happened on the test. We're taking a limit. We can't forget that we're taking a limit. And then as n approaches 5, this is going to the natural log of 0, but the natural log of 0 does not exist. Speaking a little more informally, it's negative infinity. So the natural log of 5, that's fine, it's just some number, but this does not exist. So the very natural change, you know, if the upper limit is the problem, then you take a limit as you approach the upper limit. That's a terrible sentence because limit is being used in different ways, but you get the idea. This 5 was the problem, so we approached the 5 instead of the 0. This leaves us with the case where there's a vertical asymptote between A and B. And in one sense, this case is perfectly logical because we know that if we have an integral from A to B, and we know it, and there's some number C between A and B, one of the rules of integration, we put it on the board, but we didn't really do anything with it until now, is that you can break that integral up in that way. Yeah. And, you know, with this statement written on the board, If we've got a vertical asymptote at C, we can break this up like so. And now the integral from A to C is improper, but we know how to deal with it. And the integral from C to B is improper, but we know how to deal with it. This can be unintuitive sometimes. In particular, for this to exist, both of these must exist. I keep saying exist. The more formal word is converge. If the integral is a finite number, we say that it converges. And so what we find, for example, is that the integral from -1 to 1 of 1 over the square root of x, this integral exists, even though there's a 0 right in the middle of it. We can break this up as the sum of two improper integrals. And one of these we have found already as an example in this course. We did this one. We found that it equaled 2. Here, the limit as n goes to as n goes to 0, what am I doing? I'm doing nonsense. I apologize for that. What the specific nonsense I am doing is that I'm talking about the square root on the interval from -1 to 0, even though the square root is not defined on the interval from -1 to 0. So I got ahead of myself when I said this would exist. But let's just change this problem slightly from the square root to the cubed root. Now there's not going to be a problem. We can take the cubed root of a negative number. So this is going to be x to the -1/3. So we go from -1 to n. we've got x to the negative 1/3 dx. There's no trouble with this integral. What negative 1/3 bumps up to 2/3. We divide by 2/3, we get 3/2. We are going from -1 to n. The limit as n goes to 0. 3/2 n to the 2/3, running out of room here. This is -3/2. Everything's continuous. We can just stick 0 in there. 0 to the 2/3 is 0. 1 to the 2/3 is 1. So 0 minus 3/2. The other integral, which we've no longer already done, but the limit as n approaches 0, the integral from n to 1 of x to the negative 1/3 dx. Can be taken without any, I hope, I shouldn't probably say for definite, but I hope can be taken without a lot of sweat and bother. The negative 1/3 bumps up to 1 to 2/3. We divide by that. And now as n approaches 0, there isn't any bother. Everything's continuous. As long as it's not giving us division by 0 errors, we can just stick 0 in there. We get positive 3/2. And as for the integral we started with, well, it's 0. Negative 3/2 plus positive 3/2 equals 0. And this makes a geometric sense. If you remember how area below and area above curves work. So we've got 1 divided by x to the 1/3 from -1 to 1. Let's see if I want to shade this region. It would be kind of a pain, I think, to do that. I'd need to break this into 2, and I'd say, well, here I want the area above the curve. And here I want the area below the curve. So the way area works, area below a curve up here is counted as positive. Area below a curve down here is counted as negative. And you see the symmetry. I mean, this region up here, this positive region, looks identical to this region down here, this negative region. It's, phrasing this formally, it's symmetric around the origin. So the positive area and the negative area cancel each other out. Now, where that intuition fails us is if we have 1 over x. The integral from -1 to 1 of 1 over x dx. I mean, if you look at the graph really looks like this ought to be 0. Exact same thing. This positive region and this negative region are identical. They should be canceling each other out. You ought to be getting 0. But what you actually get is that this does not exist. Because when you break it up, we've already found, as our very first example, that one of those integrals does not exist. And for the full improper integral to exist, both of these sub-improper integrals need to exist. So what we have here is, I mean, we've got negative infinity and positive infinity, but addition with infinity does not act the way addition with numbers does. You cannot add negative infinity and positive infinity and get to 0. So even though it looks the same, here we say that this area does not, that this area is infinite, that this integral does not exist. So that's part of this improper integral section. It's the part of the improper integral section that's hardest to motivate, though. Like if you imagine like marginal costs or velocities or our various applications, it's hard to imagine why we'd have a vertical asymptote. Thursday, we'll flip this on our side, on its side as it were, and we'll start looking at improper integrals like that, where instead of going up forever, we want it to go to the right forever. And this may be a little surprisingly, but this has a lot of very concrete applications that we'll talk about. So tomorrow, well, I won't give it out in class, but I'll post, we've got our sort of culminating integration test. So we'll do that next week. Thursday next week, is everyone going to be here? Okay. Thursday next week. And as far as material, we'll do a little with probability. I hope it's a good application of the integral. I don't always get to it.